In second project, we're going to let the Pintos to run a program. The objective of project number 2 is execute a user program in Pintos. Pintos cannot run the program currently, so basically it's not an operating system so far. This is background. And in Pintos, or in any operating system, it gets an argument to execute a process. Then it calls a function called process execute, and in process execute, it creates a thread with a certain function. But the problem is the body that calls process wait, it simply returns. So basically the process wait function, this function has to wait for the child process to be created and has to wait until it finishes. However, it doesn't do anything, but it simply returns. So as a result, the Pintos works like this. So in Pintos, init is a process 0. It's the mother of all processes in the world. The process ID of init process is 0. It creates a new process, and then it schedules it. However, right after it schedules it, it just exits. So if the operating system exits, how can the other program run? So in current Pintos, there is no way for the process to get executed. So final goal is on the right hand side of the slide. We let the Pintos to wait for the completion of the child process and continue. It is quite amount of work, and I'm going to explain how and what we have to do step by step. Before move on, let me explain the overall structure of the program execution in Pintos. First function is called process execute. It gets a file name. Basically, it is the name of the executable files. For example, a.out, or if you want to perform some kind of ls command, then ls is going to be supplied as a file name parameter in executing a process. And then a process execute calls a function called thread create. So via calling thread create, this function creates a new thread. So there is a thread here, and then it calls process execute, and then it calls process execute called a function thread create, and then at that very moment, new thread is created, and then it continues executing. Let's look at the details of thread create. This is a function that creates a new thread structure. So it creates a new thread structure and initialize it. And it allocates the kernel stack, and it registers the function to run. Register means put the value of instruction pointer or instruction counter to the entry point of the given process, and then add it to the ready list. Well, it sounds conceptual, so we have to look at the code. It's a simple function, and I just excerpt main line of the code. It is a function called thread create, and it needs a name of the function you need to execute, and it is supplied a default priority it wants to set, and then function name and auxiliary parameters. Let's look at the code. The first one, it allocated a single page, 4 kilobyte page, in the kernel space. And then a single space, 4 kilobyte single space, address space, it initialized a thread structure. This is going to be 64 byte or 128 bytes or whatever the thread structure size is going to be. And then it is allocated a thread ID. Every thread has a unique ID. And then it also allocates a kernel stack. Here is allocated means kernel stack. And then in the kernel stack, it initializes a various field, including the function it wants to execute. So kernel stack contains a address of the function that needs to be executed, and then the kernel puts the thread to the read list. by unblocking it. This is how a thread is created. All right, then the next step is how to start a process. So far, thread is created, and then it has got put into the read list. And then there is another important function called start process. And in start process, this is the start process, it gets a file name. So it's a name of the binary file it wants to execute. The first thing it needs to do is it loads that binary file from the disk to the memory, and then out of that binary file it obtains the location of the instruction it wants to execute. And then also it acquires a stack top pointer of the user stack. That's a role of load. If it succeeds, then it continues to execute. If it fails, then the thread has to exit. So load is very important function. It pretty much does everything from loading the binary files from the disk to memory, initialize the user stack, sets up the initial pointers, and then it calls jump. So I'm gonna go to the detail. Let me explain the details of jump instruction later on. So this is start process. Start process gets the name of the file it wants to execute, and then using that file name, it calls load. If it fails to load, then it exits. So in exit, it has to clean up all the memory chunks that has been allocated to execute the process. Let me explain how the load function works. Let's say there is elf file here. This is a.out. And there's this memory. If load is called, then kernel creates the page table for our given thread. This is page table. And then it opens the file. This is a file. So it opens the file and read the elf header. A.out is taking elf format, elf. And it has a header part here. So it first reads the elf header into memory. And then elf header contains an information about how this file is organized. From here to here, this is data, and from the location of BSS sections and location of all the binaries. So using elf header, load function parse the file and then load the data section to the data segment. So it loads the data section to the data segment and then read the text to the text segment. This is data and this is text. And then also it creates a stack for the process and then initialize it. So there was a thread structure that has been created already. So this is struct thread. So thread structure contains a pointer to the page table. This is the field of this name was page dir, and then this page dir contains a pointer to all these data structures, data field and text field and even stack field. So this is how a Pintos load a file. But loading a file actually does lots of things. It reads not only the binary files into the memory, but also it initialized data segment and it also initialized text segment for a process to run. This is an actual load function. It was to fit this function into memory, I have removed unnecessary code. So some code are missing here and some codes are missing here. Please do understand. So this line of code, this is the code to initialize the user stack for a program. And this is a code for initializing the entry point of the stack, entry point of binary variable it needs to execute. Load function contains 4 parameters, file name, and 2 variables. And this variable contains, after executing this load function, this variable will contain the starting entry point of this function. And this variable will contain the stack top of the user stack that needs to be executed. 자, 13페이지부터 다시 하겠습니다. 3, 2, 1, go. After load function finishes, the operating system reads a program file onto memory, and it initializes stack, and it initializes the data and BSS sections, and then also it initializes the text memory. This is the end of load function. I just explained the overall organization and behavior of Pintos operating system for starting process, executing process, and creating a thread. Now it's time to look at the details of what we are supposed to do. First thing is we need to implement a mechanism for passing the arguments and creating a thread. Currently in Pintos, it does not have a mechanism to tokenize the command line argument. So it just passes entire command line for process execution. So we have to modify the code. After modification, we have to tokenize individual tokens in a command line, and then we should be able to identify the thread name and find the program with file name echo. And then we should be able to push the arguments to the user stack. So in this case, there's X, Y, and Z. So we need a mechanism to push these arguments to the user stack so that the echo can use these arguments to do its job. These are 2 functions to modify. Of course, there can be many other variety of ways for you to implement this project, but in this example, I have modified these 2 functions. The most important thing is parse the arguments and push them to the user stack. So inside the process execute function, it receives the entire command line. And then it should parse the string of the file name, and then forward the first token as a name of the new process to run to the thread create function. Then thread create function will try to find the file under the name of file name and try to execute it. And another function we need to modify is start process. In start process, we have to parse the file name, and then we tokenize individual tokens, and then pushes the parameters to the user stack of the newly created process. This is a function that is provided by standard C library. You can use this function to tokenize the command line. Process executes called thread creates. It consists of 2 important parts. First one, it passes the name of the file it wants to execute as the name of thread, and then it creates a thread with the executing function of start process. I'm going to explain the details of the 2. In start process, it allocates interrupt frame, and it has to load the program and initialize interrupt frame and user stack. It initializes 2 things, interrupt frame and user stack, and then it sets up the argument at the user stack. And then it jumps to the user program through interrupt exit. The problem is that in current Pintos, it does not have a mechanism to initialize a user stack with an argument. So this is the process you have to implement in this homework, which I am going to explain from now on. Before I move on, let me explain what is getting into the kernel and what is getting out of the kernel. We all know that to getting into the kernel, we have to call the famous instruction int. If you call int, the user program traps into the operating system. If you're done with something, and then inside the kernel, you call an instruction called IRET, and then that'll get you out of the kernel. So remember interrupt and IRET. I'm going to explain details of these two instructions from now on. This is the layout of the address space. This is process address space. This is virtual address space. Virtual address space of a process. Virtual address space, a process consists of kernel space and then user space. And the user space, I did not specify that here, but there is text. And there is data. And also there is BSS. Well, for a certain operating system, the location of data segment and BS segment can be switched. Anyway, there is a stack. In normal situation, the stack time pointer ESP points to the top of the user stack here. If you call interrupt instruction, then it automatically switches the ESP from user stack to the kernel stack. It automatically does that. And then after it switches the stack from the user one to kernel one, then it starts to save the registers that has been used by a user process. And the data structure that a kernel is using to store the user's register to the kernel stack is called interrupt frame. This is very important data structure. So remember, when you execute in interrupt instruction, it switches the kernel from the user to the kernel, and it pushes registers to the interrupt frame that resides in the kernel space. This is executed in a single instruction INT. So INT is, as you see, very complicated instruction and does a lot of important things. Let me explain details of the data structure for interrupt frame. So there are 5 registers, 1, 2, 3, 4, 5, and there are 12 byte. And there are a bunch of general purpose registers. So interrupt frame, the data structure of interrupt frame is defined by operating system as well as CPU. From here to here is defined by CPU, and from here to here it is defined by the operating system. So if you look at the other operating system that runs on x86 or CPU architecture, then this part remains the same, but from this portion to this portion may vary depending on what kind of operating system you are using. Interrupt frame as reside in the kernel stack, and it stores the user process registers. Let me explain getting into the kernel we call interrupt n. When you execute a kernel function, such as interrupt handler and system core, the operating system saves the registers of the currently executing process. It is saved in the kernel stack, and it switches the ESP from the user stack to the kernel stack top, and it pushes registers. Let me explain details of pushing the interrupt frame. This is the top of the ESP. At the beginning, interrupt instruction INT switches the top stack pointer from the user stack to the kernel stack. And then inside interrupt instruction, it pushes these 5 registers. And then interrupt INT instruction finishes, and then it starts to execute the interrupt handler. Inside interrupt handler, it pushes these registers or values. So these are 12 bytes of some field, and these are general purpose registers. So after executing interrupt instruction, after executing INT instruction, and after saving all the registers that have been used by user process to kernel stack, the ESP will point to the stack top here. That's what we have to do to get into the kernel. As you see, entering into the kernel is expensive process. It switches the stack top pointer and then saves a lot of instruction. Even though some of the part is executed in hardware by single instruction, still there remains a lot of register that needs to be saved to the kernel stack by software. This is how we enter the kernel. Okay, so now let's get back to the original business, the loading. Load the program does a lot of things. First, the start process. The start process passes the program name to load, and then load instruction find the executable file using the name of the file and load into the memory. Okay, and then this is the name of the file we want to load, and this is the function entry point, the starting address of the main function that needs to be executed after the program is loaded. Load function is responsible for initializing this field. And also, load function in Pintos is responsible for initializing the ESP field of a user. So it specifies in case when the operating system starts to execute the program, this field contains the user stack top address. This is the role of the load. Okay, that's it. This is body of the start process, and I'm going to explain the details a little bit. So first, here you load the file into memory, and then at the start process, you getting out the kernel and goes into the user mode and start executing whatever program that has been supposed to be executed. So this part, there are three important instructions. 1, 2, 3. You load the executable and initialize the stack. Here it means initialize the user stack. And then when you execute the user program, you have to pass a set of arguments to the user process. This part is entirely missing. So in this red rectangle, you have to write your own code to set up a stack, which I'm going to explain shortly. And then here, the third part, it gets out of the kernel and jump to the user program you want to execute. So this part is missing. So this is the part you have to write. However, before writing this part, you have to understand the first one and the third one as well. So in getting out of the kernel, this is C statement. It consists of two basic assembly instructions. First one is move, second one is jump. So in move, you set the ESP pointer to points to the current stack top of the interrupt frame. So it'll points the top of the interrupt frame, and then it goes to jump, interrupt exit. It is specified here. So it's a process of getting out of the kernel. Let's look at the code. This says interrupt exit, and then it pops all these registers and jump another 12 bytes and calls the very famous instruction IRET. So what it does is this one corresponds to move 0 ESP. So as a result of executing this statement, the ESP points to the stack top of the interrupt frame. And then it pops all the registers, and then it skips another 12 byte. And then after calling interrupt exit, the ESP pointer will point to the stack top right here. And then it calls IRET. Then as a result of calling IRET, hardware, the CPU, pops these 5 registers automatically and restores it to the register. and then change the user mode, change the mode from the kernel to the user. So as a result of executing IRET instruction, all these 5 registers will be restored to the CPU, and then ESP will set to the stack top address of the user stack. This is how we get into the kernel and getting out of the kernel. There's one thing to remember. When you first create the thread, interrupt frame is literally empty. When a process getting into the kernel, it fills the interrupt frame with some value. So when you get into the kernel, you push the register values using interrupt, and when you're getting out of the kernel, you use IRET to get out of the kernel. But for the first created process, it has never been in the user space, so interrupt frame is currently empty when the first process is created. So for the process to be created and getting out of the kernel to the user space, operating system has to arbitrarily initialize the interrupt frame with some correct values. So that's what start process do. It initializes the interrupt frame for the newly created thread. The next thing is write a function that sets up a stack. Well, you don't have to write a function. You can just simply write the code at that region. Let me go to a few slides back. Sorry for inconvenience. Let me go back to the few slides back. Okay. All right. So now I am going to this part. Before you go into the kernel, before you actually jump into the function you want to execute at line number 3, you have to first set up a stack so that set up a stack at the user stack. This is user stack with a proper list of parameters. This is the function we are going to write. So we're going to write a function that sets up a stack. Let's consider a function. This is the address space, especially the user one. There is a text, and data region, and there's BSS, and then let's assume that ESP field of interrupt frame contains the address of stack top. So what you are supposed to do in start process is write a function to set up a user stack so that when the process resumes in its control, it pops the parameters from the user stack and runs the program. So the address of the stack top is currently saved at ESP field of the interrupt frame. So what you are supposed to do is you have to push the parameters from the stack top one by one. Let's consider this command line. It contains 4 arguments, 1, 2, 3, 4. The index is 0, 1, 2, 3. So the ARGC is 4, and the array of strings, this is 0th, and this is index 1, and this is index 2, and index 3. So what you are supposed to do is, in x86 calling convention, you have to push arguments. First, there are rules. First, you have to push character strings from left to right. So the character strings are pushed from right to left, sorry. This is right to left, right to left. And each character string has to be aligned by 4 bytes. After you are done with pushing all these character strings, you push the start address of the character strings. And then you push argv address, starting address of the arguments, and then you push the number of arguments in the command line. And then you push the address of the next instruction, which is return address. This is a rule you have to follow when you push the arguments to the user stack. This is it. So here, the number of argument is 4, and this is index 0, and this is index 1, and this is index 2, and this is index 3. Assume that before pushing the parameter, this represents the stack top. Now, we are pushing individual strings from right to left. First, we pushes bar0, and then we pushes foo, and then we pushes -l, and then we pushes /bin/ls. And the important thing is that you have to align, align this with 4 byte, because this argument string is 19 byte. So you have to add 1 byte padding to make it 20 bytes and make it 4 byte aligned. And then you pushes null terminated string 0, which means that this is the end of the argument string. And then you pushes the address of each character string, 3, 2, 1, and 0. And then you stores the address, starting address of this parameter sets. This is just represent here. Okay, and then you pushes number 4, which is number of arguments in this command line, and then you pushes return address. However, in this case, there is no return address because this is just newly created process. So once this is over, there is no way to return, just you finish the thread. So in the return address, you pushes 0 as a fake address. So I just gave the answer to this question. Why is return address here 0? Because it's just newly created process. So once you completely implement this function, then you can check if all these stack frames are properly set up using the function hexdump. This is the function provided by Pintos. By using hexdump, you can dump the hex map of the interrupt frame, and you should be able to find if your stack has been properly set up or not. Okay, this is the end of how you set up user stack. Good luck.